All right, so now I'm going to talk about measurements for a bit. And then later in the week, we'll talk more about theory, about how you calculate things. The key challenge, the biggest challenge in measuring rate coefficients is to isolate your one reaction you want to study from all the other possible reactions that the species involved can do. And it's even more complicated because you need to have, typically you have to have a way to make the species that you want to study. You have to have a way to monitor that species, and you want it to only react by the one reaction you want it to react by as much as possible, and not all the other possible side reactions it could do. And the design of the experiments have a lot to do with this. The problem is sometimes you just can't do it. So you may have to model the system, including the effects of the side reactions that are unavoidable. So for example, I showed you the case of H plus O2, a very important reaction. There's actually two reactions there, H plus O2 to go OH plus O, or H plus O2 to make HO2. And both of those reactions are always going to happen whenever you have H and O2 together. And so we would actually really like to know the two of them separately, but it's not possible. So you have to do a very complicated sequence of experiments and some modeling and stuff to try to figure out what you actually did. You have to maybe try to monitor the products simultaneously as you measure the loss of the H atoms, something. And so the experiments get more and more complicated. And that was a very simple one, H and O2. When you get to more complicated fuels, the molecules are bigger and they typically have more possible things they can do. So you get lots and lots of possible side reactions. Another issue is extrapolation. So typically your apparatus only works in a certain TP range. And if you're outside that range, you melt your apparatus, your furnace doesn't go that high, or you can't cool it enough, so you can't get below, a lot of times you can't get below room temperature with apparatus, it's hard. You need to put in refrigerators or something. And so, and the pressure is a safety thing, you can't usually exceed some pressure, otherwise you'll kill somebody. And so this is a big problem because we often want to extrapolate. So I just got a question at the break about rocket engines, running at 2,000 Kelvin and a couple hundred atmospheres. I'm sorry, I don't have an apparatus that can do that. And most of your probes, your ways of probing the reaction, wouldn't survive those conditions either. So that's going to be very limited ability to get data at that condition. So we might have to measure it at 1,000 Kelvin and 1 atmosphere, and then try to extrapolate somehow up to 2,000 Kelvin and 100 atmospheres. And you can imagine that the extrapolation can be pretty difficult. But that's, anyway, that's what people have to do. But that introduces a big errors. So when you look in the kinetics databases, people report measuring a rate coefficient. They'll report the range of temperatures and pressures they measured it over. And then somebody later will come along and they'll draw a straight line through it, Arrhenius, and they'll tell you, oh yeah, just use this number up here at 1,000 Kelvin higher. And maybe it's right. But you don't know. All right. And then even if you have very good help with theory, the theory can help a lot sometimes to know what the shape of the extrapolation curve should be. But it's still extrapolation. And so even with the theory to help you, you still increase the uncertainties the further you get from the real data. All right, so here's some important techniques you should know about. One is called laser flash photolysis or pulse laser photolysis. This is a method that was invented, I think, by a guy named Porter, got the Nobel Prize for it a long time ago. And this is a way where you use a flash of light to suddenly create a bunch of, say, free radicals or some reactive intermediates. And because you can buy a nice, powerful laser these days, you can actually make quite a lot of the radical, enough that you can measure it. But the radicals are very reactive, so a few microseconds later they'll be gone because they all react. And so if you have fast time constant on your measuring device, you can measure them appear and measure them disappear. And the time constant that they disappear on is the rate of the reaction of the radicals. So that's a really good method. Shock tubes is another method where you can suddenly make a lot of reactive stuff. The way that works is you run a shock wave through your stable molecules, and the heat, the temperature jumps so high that some bonds break in your regular molecules and make some fragments. And those guys, some of those will be reactive intermediates you want to see. And then you can monitor them disappearing. Another way is more simple. It's called flow tubes. You just mix up reactant A, reactant B, and you just flow them down the tube, and you look at different distances down the tube and see what you see. And you'll see like different products appearing. So that's a kind of traditional way. And then you can do static studies where you just, this is like you put some reactants together, you stick it in the oven, you cook them for a while, you take it out, you see what you made. It's like baking. And so those ones typically you don't have time resolution, but what you have then is product distribution. So you can measure all the products you made. And so we say chromatography, for example, or infrared spectroscopy. And so you can measure lots and lots of products. So that you generally have a trade-off that some methods are very good at time resolved, but typically only probe a single species. And then other methods, you lose all the time information, or most of it, but you get lots of species. Things like chromatography, for example, NMR, they can measure a lot of species simultaneously. Whereas laser spectroscopy, typically you have a laser that's tuned to see exactly one reactive intermediate, and that's it. And so all you see is the time trace of that one species. You're not really sure what happened with everybody else. If you have a very expensive and fancy lab like they have at Stanford, maybe you can measure 4 of them at the same time, or something like that. Okay. But it's, in general, that's a hard way to do it, to get a lot of species. But you get very, very great time resolution because the laser methods are very excellent time resolution, and you get a lot of data points. All right, yeah, so usually you can either measure the time dependence or the product distribution, and most apparatuses can't do both. The product yields, if you do measure the products, you often need absolute calibrations. And calibration is the bane of an experimentalist. So if you measure, say you do one of the shake and bake experiments, you cook your stuff for a while, you see what you made. Say you put some fuel in there and you cook it and you see how it broke up and just other things. Now I have a whole lot of other stuff in there. Say I shine my infrared laser through, or infrared spectrometer. I measure all these infrared peaks. Now each of these peaks corresponds to some different molecules in there, but the response factors, exactly how much amplitude I get for a certain amount of each thing, I don't know. So I have to go get authentic standards of every molecule and stick them in there and measure the infrared spectrum of all these different molecules. And then I can add them up and weight them by their concentrations in order to figure out what I have. But that could be pretty laborious if no one's done those molecules before. I have to go actually synthesize them or buy them. I have to go stick them in, measure the infrared spectrum. So you can see, after you do this for a little while, you might get like, oh, this is really a pain in the neck. The favorite method is what's called pseudo first order. This is the only method I know of that you don't need to know any absolute calibrations of the intermediate. So this is much, much more popular because of that, because you avoid the whole need for calibrations. And the way it works is if you have a reaction, x plus y goes to products, and if x is much, much less than y, then this is the solution of the differential equation for the decay of x. And so if I have y as a stable molecule in high concentration, just like here actually, right? I had radical plus stable. Suppose x is a radical, y is a stable. Then all I need to know is the ratio of x to the initial amount of x. So I need just the ratio of signals. I don't need to know the absolute calibrations of either one, because it's going to cancel out. And all I need is the absolute value of y, but if y is a stable molecule, I know how much I put in there, so I'll know. So this is the favorite method. So let's just show some experiments. This is laser flash photolysis with laser-induced fluorescence detection for OH reacting with something. And so you put something in there that's an OH precursor, you put in some reactant, you have some buffer gas, usually helium, then you blast it with an excimer laser, it makes the OH radicals, then the dye laser is tuned to an absorption of the OH that makes it fluoresce. You have a photomultiplier tube which detects the fluorescence photons. It has a filter in front, so it all sees is the fluorescence of the OH. And then you measure that at short times you'll see a lot of fluorescence of OH because you made a lot of OH. As you wait, the OH reacts with your reactant gas, and the concentration of OH will be smaller. And then you get less fluorescence photons when you blast it with a laser. I really don't know exactly how much OH I made, but I know the relative. So initially I had a lot, later I had less. I do the ratios, I get the rate constant. So this is a nice thing. This is often done this way, where you have a pulsed laser and a pulse laser. It's not really the best way. It'd be better if this laser was continuous, so I get the entire time dependence of the OH in a single shot. But oftentimes you don't have the right lasers to do it, because you need to have a continuous source of light at that wavelength, which might be hard to make. And here's the actual data from this experiment. So they varied the time dependent, the difference between these two laser pulses, the time between them. When the time between them was very short, you got a big signal. When you make a long delay between this signal, the creation of the OH, and when you probed it, then you get a smaller signal. You can see you can fit it to a single exponential, and from that you can extract the rate coefficient. There it is. Okay. So this is, for example, the reaction of OH with SO2. It's an important reaction in the atmosphere. This is the way that they did it. They made the lasers. They monitored the OH by LIF. All we need to know is the signal's proportional to how much OH we have. And so you first measure the OH fluorescence as a function of the time difference. You plot it in a log plot. It's almost a straight line because it's an exponential decay. Figure out the slope of the log plot. That's K times concentration of SO2. Do it with different amounts of SO2. And the slope of this guy will be the actual K, the rate coefficient I wanted. So just run the same experiment, lots of different pulses, lots of different amounts of SO2. Actually, I might want to do it at different temperatures and different pressures as well, and do it all together and get the whole story. Here's another one, OH plus acetone. And they did the same thing. And the only calibration needed is for the stable molecule. So in this case, they need to know how much acetone they had. So they measured the acetone by looking at some optical absorption of acetone. And somebody had already done the calibration where they had measured the absorption cross-section of acetone, so they knew what it was. And often the biggest source of error in the K is actually knowing the concentration of the stable species when you do this, because that comes directly into the calculation. Right? When I made this plot here, I needed to know these absolute numbers of how much SO2 I had. You can also, instead of using laser-induced fluorescence, you can use mass spectrometry to detect stuff. So here's an experiment, actually this is very similar to what I do in my lab, where you flash with an ultraviolet laser, you make a column full of radicals by your photolyzing your precursor. And then the radicals react with some stuff, and they make some products that have a different mass. And so if you monitor that mass in your mass spectrometer, you'll see that changes with time. And from the time changing of that, you can figure out the rate at which the OH must have reacted, because it corresponds to the rate of the rise of the products. And then you can, if you know how much of the reactant you had, you can do the same procedure again, pseudo first order. If you happen to have access to a synchrotron, then you can do really fancy mass spectrometry where you have a photoionization mass spectrometry. This is nicer because normal mass spectrometry uses electron bombardment to ionize the molecules to make the mass spec work. But electron bombardment can actually break the molecules. So sometimes you'll be completely confused because you're seeing masses different than the masses of the actual products you had because you broke them. But if you do it with a gentle photoionization, you have just barely enough energy to knock the electron off, and usually it won't fragment the molecule. And so then you can know what's called the parent ion mass. You can be sure that was really the ion that you had to begin with. Sometimes you can find several isomers with the same mass, and by doing this, if they have different ionization thresholds, you can vary the photon size that's doing the ionization. At low photon energies, you only get the one that's easy to ionize. Then you increase it, you'll start to see all of them ionizing at high photon energies. And then you can deconvolute it and figure out the relative yields. And so this guy, Todges, who's now the editor of the International Journal of Chemical Kinetics, he's been really famous for this. He's published a bunch of papers in Science where he's seen a lot of weird isomers that people had speculated might exist, but nobody could see them before. And he has this tunable photoionization mass spectrometry at the synchrotron. He's able to see a lot of them. And so this one is for ethanol, which is a organic chemists thought it existed, but nobody could see it for a long time. So he was able to see that it has the same mass as acetaldehyde. In fact, it's a famous keto-enol tautomerization that these two guys can both exist. He's able to measure them both separately this way. This is another apparatus he has also at the synchrotron. And this one was for CH2OO, which is called the Kriege intermediate. Again, it was an organic chemist speculated there must be some reactive intermediate of this formula to explain what they saw in ozone chemistry, but nobody could see it for years and years. So it was speculated in 1949. Wasn't observed until 2012 by these guys because they had the right synchrotron. But once you can see the reactive intermediate, then it's relatively straightforward to go ahead and do the kinetics and figure out everything it reacts with and what the rates are. So that's been a whole bunch of papers following up on this paper. There's a whole lot of other papers that have been tracking down all the reactions. You can see all the different isomers of the Kriege intermediate. You can see there. This is another really important reaction. This is the OH radical reacting with acetylene. A lot of flames have acetylene in them. You have a lot of OH, so you have reactions like this happening. This is a pressure-dependent reaction, so you have to measure it as a function of temperature and pressure. Here you can see that the rate actually is almost linear with the pressure, which means it's really pressure-dependent. It's really strong. Here's at higher pressures, it saturates. You see that originally it's very sensitive to the pressure, and then it goes flat. And so then you can work out that formula I showed you before about how the rate depends on the pressure at low pressure, but it becomes insensitive to pressure at high pressure. And we can work it all out by the shapes of these curves from measuring all the rate coefficients at all those different conditions. You can use absorption spectroscopy to measure the radicals. Instead, this is with a monochromator. This is a very difficult experiment because it's a second order reaction. So this is this radical reacting with itself, allyl plus allyl. Because it's not pseudo first order, I do need an absolute calibration. So 3/4 of this experiment is trying to figure out exactly how much allyl radical they had in there. So they had to figure out all kinds of different ways you can try to figure out what it is. And actually my group did the same measurement, try to measure this reaction also. We did it where we started with, what do I do with my chalk? Now I'm in trouble. There we go. I have one little stub of chalk. This is it. All right, so what we did, we started with this molecule, C3H5I. We photolized it with a UV photon. It made CH3H5, the radical I cared about, plus an I atom. And then I had two lasers. I had one laser that was tuned onto this molecule, and I had another laser that was tuned onto the I atom. And the absolute absorption cross-section of I atoms had been measured previously by somebody else. So if I can measure exactly how much light was being absorbed by the I atom, and I assume that these guys were formed one-to-one, then I could infer how much of this guy I had. So I can get an absolute calibration for it. So with this, I was able to get a number for this. This is not me. This is another guy's paper on the same thing. So I don't know how they did it. Here we go. Oh, so this is actually, yeah. So this is me. This is with the I atom one. These other guys, there were several papers previously doing this where they worked out different clever schemes to try to figure out how much of the radical they had. There's called actinometry. There's like a whole field about how to do the calibrations, where by making the radical react 100% with something that you can then detect some other way, and you know the absolute calibration for that thing, so therefore you can infer the absolute calibration of the first one. But of course, you can be screwed up because there might be a side reaction. Anyways, it's quite a complicated thing. You get a lot of different numbers. So for the second order reactions, the dispersion of measured values is quite large, whereas the pseudo first order ones, it's usually very tight because all the experiments will get the same number because they don't depend on the calibration. Calibration adds a lot of uncertainty to your thing. Another tricky thing is that in these experiments, usually what you have is you have a region that's illuminated by a light, typically like a UV laser. You blast the laser beam down through your cell. You make your radicals. Then you monitor the radicals in here. So here I make a nice C3H5 radical, and it can react with another C3H5 radical. These two guys can bump into each other and make a reaction. That's what I'm trying to measure. But this guy could also diffuse out of the beam, and so he's gone. And so very often in these experiments, what you'll see is combined first order and second order kinetics. First order kinetics is a physical process. It's moving out the beam. And then you get second order kinetics because they're recombining with each other. And typically, initially, it'll be mostly second order kinetics because you have a high concentration. But as they react away, it gets more and more first order because it's less and less likely they're going to hit each other because there's not many of them left. So then you have to use combined first order, second order fits. And you have now two parameters, one for the first order, one for the second order. Anyway, so you can imagine. But you can do it if you're really determined. A nice method that people have invented for measuring radicals which are present in very low concentrations is called cavity ring down spectroscopy. This one, what you do is you have two mirrors which are really great mirrors. So great that if you put a pulse of light in, it just rings back and forth, ding, 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 maybe 1,000 times. And what you can do is you can look with a very sensitive detector over here. Every time it hits this mirror, a tiny bit of the light leaks through the mirror. And if you look on the back side, you can actually see a few photons coming through. So if you send a pulse of light in, it goes ding, 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 ding. And over here you see dung, 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 dung. And that's getting weaker and weaker as time goes on. And by measuring the decay rate of how fast that goes down, that's because some of these photons in here are hitting your molecule. So in here I have a little bit of tiny bit of HCO radicals. And some of these pulses of light, every once in a while, one of them gets absorbed by an HCO and it's gone. So the next time this comes back, this pulse is a little bit weaker. And I measure that absorption. That's actually, you can infer from the time dependence of the pulses of light coming through, you can infer what the actual absorption concentration is. And you can get very, very weak absorbances, much, much weak. It's really, essentially, you have a path length that's this distance times maybe 1,000, because it goes 1,000 times. And so if you look in Beer's law, it's E to the negative absorption strength concentration, which is tiny, and then L. If I can make L really huge, then I can make up for the fact that my concentration is tiny. So this is a good method for very sensitive kinetics on radicals. So this is what the system really looked like. We have like a photolysis laser to make the radicals, and a detection laser to come through, and then you very carefully would measure the photons coming through to figure it out. And this is the absorption spectrum of the HCO radicals. And so they measure the rates. This is another one. They measured the product yields by laser flash photolysis. So this is a reaction, singlet methylene with hydrogen. This is a pretty important reaction in a lot of hydrocarbon systems. And it makes methyl radicals. And so they measured with one wavelength the fluorescence of the singlet methylene, which was decaying away. And then with another wavelength, they measured the fluorescence from the H atom that was being formed. And then if they had to do very complicated absolute calibrations for both these guys, and then they could actually infer the rate, which they did. This one was for, this is an interesting one. So this is ethyl radical plus O2. Let's see if I can explain this. So these are the sequence of reactions that people think should happen. Ethyl radicals should react with O2 and make an energized adduct. The energized adduct can have a collision and lose some energy and get stabilized. There's this thing called a peroxy radical. It could also just directly react and kick out an HO2 and an ethylene. Or it could, this guy, once it gets stabilized, could have a second collision, get energized again, and kick out ethylene and HO2. And it seems a little strange, actually, overall, to write this way. But this is the truth. It actually acts this way. And they can infer separately all these different rate coefficients by careful analyses of seeing all these different products. So these guys observed the HO2, and you can also observe the peroxies. And so you can actually, if you do careful analysis of the whole system at all different conditions, you can get regimes where each of these different reactions is sort of isolated from the rest to get all the rate coefficients separately. And then shock tubes are very important for the high temperature. This is the most convenient way to achieve the high temperatures of combustion without burning up your lab. And so the way this works is you have a big long metal tube, a pipe, closed at both ends. You put like a little piece of plastic or aluminum foil, and on one side of it, you put a lot of high pressure gas. On the other side, you have your reactants at low pressure, and they're all stable. You increase this pressure high enough, or you poke this with a little pin or something, and break the diaphragm. And when this high pressure is immediately next to this low pressure, it quickly develops into a shock wave. And the shock wave travels down the pipe, and it bounces off the back and comes on back. And in the region down here, this gas got heated up by the shock, and then the reflected shock heats it even more, and the temperature is very high. So the temperature can be 1500, 2000 Kelvin, 1200, and you can control what temperature you want by varying the pressure ratios and exactly what the gases are. You can figure out what the temperature would be behind the shock. And so you know what temperature you made, and then if you can put some kind of monitor here that can measure the molecules, then you can measure the time dependence. So when you suddenly heat a molecule up to 2000 Kelvin, a lot of times the weakest bond of the molecule will just break because the energy is so high. And now you have two reactive intermediates, the two fragments. And then if you have lasers, for example, that can monitor the fragments, you can monitor the time decay. You can have it mixed up with some other stable molecule that doesn't break, and the fragments will come and react with that. And so this is a guy, particularly a guy named Ron Hansen at Stanford, is very famous at doing this, and has a very big group of people who do a really nice job with this. You can also do a different variant on this, where you can, instead of having a pipe like this, you can have like a little valve, and you can suddenly open the valve and suck all the gas out, and then measure all the products. And so you do chromatography and measure all the products. And so people like Wing Tsang at NIST is very famous for doing experiments like that. So that you have to infer from the final products. It's sort of like the cooking experiment, except now I cooked it at 2000 Kelvin, which might have been hard for me to get an oven that could do it. But now I can just do it with shock. Also, what's interesting about the shock wave is that you have a certain amount of time. So the shock wave comes down, it bounces back, but on the other way, there's a rarefaction wave that's bouncing the other direction. It's going back and coming back. And at some point, that rarefaction wave is going to come down and hit the region that was heated, and it's going to cool it back down. So you have like a shock heats it, and then the rarefaction, the expansion wave, quenches it back down. And that whole time scale is not very long. So this is it's a high temperature but relatively short time scale, which is good because high temperature, long time scale, everything will go to equilibrium. And you wouldn't measure any product distribution except the equilibrium distribution. But high temperature, short time scale, then the kinetics is not quite over, and you actually can measure a lot of interesting things from the product distribution. But sometimes it's a little bit annoying. You have to make your tube very, very long to give it a long time before the rarefaction wave comes. If you want to do a long time scale experiment, you might have to give very, very long tubes. So at Stanford, for example, they have tubes that are like as long as the stairs here to try to just make it more time before the rarefaction wave will get there. So here's actually a picture of Stanford. See, it's really long. And the Stanford group has a lot of nice lasers, so they do probes, measure many of the different species by direct absorption near the end wall where the reflective shock is. Here's some examples. This is by Vasu, and he was measuring, which one was he trying to measure? CH3 plus OH. So this is tricky, right, because it's two different radicals. He needs absolute calibrations for at least one of them in order to be able to measure the rate coefficient. And also there's a lot of side reactions, so he has to model these side reactions. And what he does is he does a sensitivity of how much each of these side reactions could possibly affect the amount of OH based on the model predictions. And so if you get in a regime where this one reaction here is the dominant one, which happens to be the OH plus acetone reaction in this case, then if you measure something at this time scale, you can say it's mostly due to OH plus acetone. Now, those guys might do is they might measure that one first. Now we understand OH plus acetone, so I could put in a very firm number for that rate coefficient. And now I could go to a different time scale and try to figure out, say, what this reaction was doing. And then they do careful error analysis and figure out from their experiment measurement of the OH, what error bar they could tolerate on these different rate coefficients in order to still fit their data. And if you're clever about doing this, you can set it up so you can really narrow in the error bar on one rate coefficient separately. If you don't plan it carefully, most likely you'll be sensitive to several, and you won't be able to make any firm conclusion whatsoever about what the real rate coefficients are, because all you're measuring is a combination of several rate coefficients together. But if you do it cleverly, you can isolate them and get one at a time. This is another one where they, the way the experiment worked, they started with terbutyl hydroperoxide. If you heat it up, it makes OH radicals plus two butoxy radicals. They measured the OH by using this particular line of this OH electronic transition at 306.7 nanometers. And then they did a detailed model of the whole kinetics, added in some acetone chemistry, figured out stuff about the OH precursor concentration, did a very detailed uncertainty analysis, and able to figure out several rate coefficients. You have to do uncertainty analysis to say, well, I have, say in that case, he has 4 reactions in his model. You have to say, well, what happens if I was wrong by a factor of 2 in one of these reactions? What would the effect be on my interpretation of the experiment? And they have to go through and run through the cases. So he runs through all the different cases where if 2 of the reaction rates were wrong by some amount, would that be enough to actually make an effect, or can I still be firm in my conclusion about it? With things like 4 reactions, you have a chance to do this. If you had 10 reactions that were all contributing a lot and they're all uncertain, you'd have no chance. So the key is actually good design to try to minimize the number of reactions that can possibly affect you. Because everything's uncertain in life. All right, and there's the Arrhenius plot. You see some pretty funky things. This is one of these ones where it looks like it goes up. It's like the rate, as the temperature goes down from left to right, the rate goes down as normal, but then it looks like it tails up a little bit here. And there's like a dispute. Different people measured it. Some people did theoretical calculations. They look like it's a random plot. They have no idea. So this is one where it's really good to have a good experiment to solidify what the real truth is. And this is another very important reaction. Formaldehyde is made in high concentrations, a lot of combustion systems, and it's toxic. So you really don't want to make it. So it's very important to understand what happens to it. All right, and then flow tubes. So this is a flow tube is pretty simple. You just, let's see, flow in your reactants, you flow them down, and you flow out to the pump. And you can generate, you can run a discharge that will create radicals. So you can run microwaves, make it like a little mini plasma. When you run some gas through that, it actually has such high temperatures in the plasma that you can blast some molecules apart and make radicals. Then the radicals formed, if the concentration is low enough, they won't really recombine very fast. So they'll flow down with the flow of helium as still atoms or radicals, and then they can go and attack your molecule further down. So you can create them in like a high temperature region, but you have plenty of time for them to thermalize back to your temperature so you know what the real temperature is. So this is a nice method. Here's another flow reactor. This is one, actually one of my current postdocs I did. He fed in gas, it was butanol, an alternative fuel, and he cooked it in a furnace as it flowed down here. Then the gas came out of the furnace. Most of the gas went back this way, but a little bit went through a little pinhole and another little skimmer and into a high vacuum region where he shined it with vacuum ultraviolet light from a synchrotron and measured the mass spectrum. And so this is a way to know what mass products he made from pyrolysis of butanol. And you see the butanol going away, formation of butene, formation of methyl radicals, formation of propene, all kinds of stuff. And so you can vary the temperature, see how the products change. So these are all versus temperature. So you get a lot of information to try to analyze and figure out what happened. In this case, there's like 150 reactions that are important. And so this is, but he also has like 60 different species and lots of different temperatures that he measured. So you can start to try to unravel what the story is. This is another one he was able to determine some rate coefficients pretty well determined by changing the temperature and changing the pressure. At higher pressures, the butanol falls apart faster because it's the reverse of the stabilization. So if I started down here with something, if I have a lot of pressure, it'll go up faster up to the top. If I don't have enough pressure, it'll take a long time for it to get heated up to fall apart. And so when you change the pressure, you see how much it changes the rate constant from 5 torr to 760 torr. It changes it so that it's almost equivalent of a couple hundred degrees temperature difference. This is another synchrotron one where if you change the photon energy, only the species that easily give off an electron will get ionized by low energy photons. And as you increase the photon energy, lots of things will get ionized. And so typically you'll see like a sum of all the things with the same mass, but they all have different ionization thresholds. And you see like a staircase. You ionize one, then you ionize the next one, you ionize the next one. And you can deconvolute that to understand if you have several species the same mass. Normally mass spec wouldn't be able to tell the difference, but this is a way you can use it to tell the difference. All right. And then in the old days, people would just cook stuff. So a guy named Walker did some really nice cooking experiments. He just cooked up some fuels with some oxygen, put a little bit of hydrogen there, just cooked it for a while, and then he did analysis. And by doing it over and over again in lots of different conditions, he was able to actually figure out a whole lot of things about the peroxy chemistry, which has stood the test of time, are now in the textbooks about how peroxies work. And that turned out to be important for understanding the ignition system, just like the H2O2 system here. So this one we talked about already. And if you're interested in the hydrogen oxygen system, this is a very important system. There's a nice review in 2005 here. And you can see that H plus O2 reaction is the dominant. Everything's most sensitive to that, and then lower sensitivity to the other reactions. And so because that's so important, a lot of people have tried to measure it to get really good numbers for that reaction. So this is a paper by Hong et al., referring his other papers, a lot of papers here, showing the rate coefficient at high temperature. This is like 3,000 Kelvin down to 1,000 Kelvin. And you can see lots and lots of data points, a lot of experiments. And there's a paper by Burke et al., 2012, explaining about the details. This is such an important reaction because you're so sensitive to it. So if you were 10% off in this rate coefficient, you'd mispredict like the ignition or the explosion of H plus O2. To try to nail it down, some people tried to measure the reaction in reverse. So they started with O atoms and OH and measured the formation of H atoms. It's kind of a weird experiment. But you can do this one at low temperature. So the problem with the previous experiment is the reaction only runs in this direction at very high temperature. But this reaction runs even at low temperature. So this is down here at room temperature. And so that helps to fill in the low temperature branch because you know the forward and reverse rates are relate to each other at every temperature. And for something like this, you know the thermochemistry really well. So you know if you can measure either way, forward or reverse, that's equally good because you can fill in the equilibrium constant to get the other one. And so this was a good way to nail down the temperature. So they can have the error in the log of K to be this small over the whole range from 250 K all up to 3,000 K. It's pretty rare to have such good accuracy over the entire range. The second step is important too. The O atoms react in the H2. And so here's this big long story about this one. The O atoms were measured by resonance fluorescence. This is a tricky technique. You make some other O atoms. They fluoresce. Their photons are exactly the right wavelength to match the absorption of the O atoms. So and then the O atoms don't have a very complicated electronic spectrum. They're such a simple molecule. So they just fluoresce again at the same photon wavelength. So you see, it's very weird. You're making the photon in your lamp. It's hitting your O atom in your reactor. That's exciting it. It's fluorescing again a short time later, and you're detecting it off axis with a phototube. This is the way the apparatus works. This is a very tricky experiment because let's see if I explain this. The wavelength of the light, your absorption line is pretty sharp for an O atom absorption. So this is O atom. But the width of this depends on the Doppler width. It means how fast is the molecules moving. Because of the Doppler effect, if it's moving towards you or away from you, you have a red shift or a blue shift. So you get a little tiny width here. Do this Doppler thing. If it's hot, if the O atoms are hot, the spectrum will look like this. It'll be broad because of the Doppler effect is big. So now you have to consider the temperature of the lamp and the temperature of your reactor, and which of them is broader than the other, to figure out what fraction of the photons should be absorbed, because they only are absorbed when the lamp and the reactor guys are on the same wavelength, right? That's the only ones that will be absorbed. Does that make sense? So anyway, the interpretation is actually way more complicated than you might think. And the lamps are also a problem. They have a lamp. Let's see what a lamp looks like. So in here, I have some O atoms, and they're really hot. But then I might have some region near the wall here, near the window, so I have a window. And my lights, I'm trying to get light to come out. This is going to go to my reactor, where I have some O atoms also. So I have another window over here, say. And then I'm going to look, I have a third window over here, and here's my photomultiplier tube. So the way I want this to work is I want to make a photon, I want it to go through, I want it to get absorbed, and then I want it to get fluoresced into my detector. But the problem is if I have a cold layer of O atoms here, they might absorb the photons before they go into the cell. And their Doppler width will be different than the Doppler width of the hot ones in the lamp. So you can get a very strange shapes, like you can have things like this, that the light coming out of your lamp looks like this. It has like a dip in it. And then your absorption in the reactor is at some different temperature. Maybe it's like it wants to absorb like this. And now you have to figure out what the heck, how many photons are really being absorbed. So there's a calibration, again, is the key thing for this. Anyway, some people make it work, and they're able to measure this correctly. And then these guys did it a different way with laser flash photolysis, and they get basically the same result. So it means the first guys did it right. It's H plus O2. And this is very important because this is competing with the reaction that made the radicals. And what's tricky about this is it actually depends on which collider you have. So some molecules collide and take away the energy faster than others. And in particular, water vapor turns out to be really good at quenching HO2. So water vapor has very similar vibrational frequencies to HO2. And so when they hit each other, there's a high probability of a vibration-to-vibration energy transfer. And it'll take away a lot of energy in one fell swoop. Whereas if you only did an experiment, say, in helium, helium doesn't really match up very well with HO2, and it's not very effective at taking away the energy. So you need less water than you would helium in order to quench this. So the rate actually has a dependence on which stuff you have. So in your experiment in the lab, you might have used helium because it was easy, because water vapor is a pain in the neck in the lab because it condenses. But then in the real combustion system, you have a lot of water vapor being formed. You're making all the steam. And so then you have a confusing situation. This is still kind of controversial, actually. But people have spent a lot of time to try to understand it. This is very important for understanding the kinetics. And these are different measurements for the different colliders. See, you can see even nitrogen has a significantly different slope than these other guys. And then here's the data for water. This is a flow reactor for high pressure. Now, high pressure, you have to make everything really tiny because you need really thick walls to hold the pressure in, otherwise you'll have an explosion. And if you need windows, you're in big trouble in a high pressure system. But some people can make it work. So there's a group in Germany that was able to do up to 950 bar. So that's worth, I don't know, it's probably worth a couple exclamation points. And so this is needed if you want to get into the saturation regime. For these small molecule reactions, it's hard to get high enough pressure that you're really saturated. So if you want to see it, you have to really push it. At that case, you have to worry about your absorption spectra are perturbed by the fact the pressure is so high. And so then you have to check all your calibration factors and stuff again. So it's another kind of sort of complicated story about doing these experiments. But anyway, they got it. You can see this is the time profile of the absorption of the HO2 is being formed. HO2 is rising. And then the fall-off curves at different temperatures. And depending on the temperature, you need different amounts of the Beth gas to capture the H plus O2. And there's a theory to understand that. And if you can do a reduction and everything falls, all the data basically falls in one line, it means you really understand what's happening. And there's a long story about this in 2012. Lots and lots of people trying to measure this. And you can see that they basically all agree, but still errors maybe a factor of 2. Uncertainty is a factor of 2 in that number. I talked about that already. It turns out when you look into this in some detail, that the symbol model I gave you before isn't quite right, and you have like another factor f that corrects it, and this is what that factor looks like. And it has to do with the, sorry, where am I going? When you look at the shape of this curve, it always happens at the points that are underneath the curve in the knee. So the model knee is too sharp, and the real is more broad. And that's many systems show this. And there's a theoretical analysis of why that happens by Troa, and then he proposed that this formula corrects for that. And this turns out to fit very well for lots of data. So many times in your kinetic models, they'll report Troa parameters, which are these like P stars and C and stuff like that.
Can you tell us what the theoretical reason is?
I'll come back to this later in the week. It's very detailed. This is another one. Some of these reactions have this non-Arrhenius behavior that they increase the rates at low temperature, and then they also increase at high temperature, and there's like a minimum somewhere in the middle. This is really confusing. And it has to do with, at very low temperatures, you form complexes, like van der Waals complexes first, but at higher temperatures, they're not stable, so they fall apart. And so you can get this kind of strange behavior. Sometimes you get new channels open up as well. But this is a very common comment. Difficult to discern which, if any, of the high temperature determinations is reliable. More measurements needed. You read a lot of kinetics papers like this. So, when you do a measurement the first time, usually your uncertainty to begin with is 5 orders of magnitude. You have no idea what the rate coefficient is. But then after the first measurement, then the third and fourth and fifth group comes along and tries to measure it, and they never all agree with each other. And so then you're trying to figure out, well, what was subtly wrong about some of those measurements to make them disagree with each other? What was the systematic errors and stuff like that? And then there's a committee that tries to rationalize this and figure it out, and figure out what happened, and recommend which value is the truth. And then once in a while, they can't figure it out. And then you get comments like this, that in some temperature region, everybody agrees, but somewhere else, there's a disagreement, and people don't know. Did somebody have dirt in their apparatus? Is there some side reaction that we didn't think of? Yeah, who knows? So anyway, that's what the kind of hard work of the kineticist trying to really nail down the numbers for the rate coefficients. This is a very important reaction. You make a lot of hydrogen peroxide in low temperature ignition systems, and knowing exactly this rate is very important. This is actually difficult to measure too. And so there's still a lot of work on this. And you can see that the theory doesn't really match the experimental data. And so this is one of these ones that's still an unresolved problem. And part of this is the experiments are hard because it's a second order reaction, so you need to have absolute calibrations, which is always a pain in the butt. And people try to measure both directions. They sort of agree with each other, but again, not really exactly, so something's not quite right. And this is kind of like active research of trying to, again, get the error bar smaller and smaller. So you have the number, it's a some error bar. And then as time goes on, people gradually bring them in, and usually they just converge. Sometimes you find out there was some gross mistake in an earlier number and the thing jumps to a new value. But usually it's just that the error bars are too big because of some subtle problem about the experiments. Particularly these ones with calibrations. That's a lot to do with how you do the calibration. It's easy to have 20, 30% errors and those kinds of things. So this shows that this case, by 2010, this is starting to get pretty good, that lots of people's measurements are all falling in the same line, so that at least the high temperature part of the H2O2 dissociation is really well determined now. And notice the range of scales. So this is from 10 to the 6th to 10 to the 10th. So there's 4 orders of magnitude change in the rate coefficient. And so this is the kind of thing in kinetics you probably don't have so much in the physics, right? In fluid mechanics, viscosity might change by a factor of 100. Maybe more likely, maybe a factor of 20%, depending on your conditions. In kinetics, you have many rate coefficients that are varying by many orders of magnitude as you vary your temperature and pressure conditions throughout the flame. So you get wild changes in the chemistry. So you think you understand something in some temperature region you're used to working in, but you go to some different temperatures, it can really be completely different. So here's a good example. So this is all pretty high temperature. This is 4 orders of magnitude. If you go down lower temperatures, this keeps going on. So you get, you might go over 8 orders of magnitude in this rate coefficient over the range of flame. All right. Last few minutes, we'll do quickly some sequences. So far I've only talked about small molecules, but now let's talk about bigger ones. So this is, say, alkanes. So I have an alkane. The most important reactions are the alkane reacts with like OH, H atoms, O atoms, and to make radicals of the alkane. And this happens pretty fast if you have a lot of radicals. So once you get the H plus O2 reaction running, you make a lot of radicals. The radicals are very reactive. They attack your alkane, your fuel. The fuel molecules, say, for example, propane, it can break to make propyl. The propyl radical will itself spontaneously decompose by a reaction called beta scission, where it breaks the bond beta to the radical site and makes a double bond plus a radical. And if you have a longer alkane, it just does this several times and spits out a lot of ethylenes. It ends up making a methyl or making a other small radical. You can also, these original radicals are very reactive, and they'll pull any H off the fuel. So they could also pull off the middle H, make isopropyl, and when this guy falls apart, it'll make propene plus an H atom. So you get the H atom would go on then to do some more chemistry. The methyl radical is relatively unreactive, so it sit around. And now I have a mixture of propene and ethylene. And so this is the common story, is that for above about 1,000 Kelvin, all the fuel radicals you make just immediately beta scission and make a whole bunch of alkenes, plus a smaller radical. And the main products you get at the end are, I should say ethene. Sorry, this is a Microsoft Word for some reason doesn't like ethene, it makes it ethene. It's ethene, propene, and then you get methane from the methyl radicals and H2 from the H atoms. So for example, octyl radical breaks up to make 4 ethylenes, ethene. Isooctyl does a little bit more complicated thing where you get some ethene and some propene. This is very important in the steam cracker business for making plastics. You take some alkanes, you put them in a reactor, you make a mixture of ethylene and propylene. You use that to make polyethylene and polypropylene, the plastic bags and stuff that we see every day. And of course, they care a lot about exactly how much ethylene they make and how much propylene because they're selling it as a product. And so there's a whole big community about trying to measure that, understand that in detail. It all has to do with exactly the same reactions here. Now when we put oxygen in, it gets a little more complicated. So for example, if I start with the methyl radicals I made from falling apart the big stuff, I'll make some ethane from the recombination. But I also can make, when these guys recombine, it's one of these systems. Or now it's CH3 plus CH3. Falls apart to make, can combine to make C2H6, but at low pressures can fall apart to C2H5 plus H. And actually, this one's drawn backwards, so it should be the other way around. No, it's not quite right. It's like this, actually. So at low temperatures, it goes like this. At higher temperatures, you have a Boltzmann population up here, and some of it can go straight across. But some of these guys here are C2H6 excited, and they can have collisions to go down. So you make a mix of ethane and ethyl radicals. And then the ethane you make can also make ethyl radicals. The ethyl radicals typically spit out an H atom and make ethylene very quickly. And then the ethylene does a strange reaction where it reacts with the O atoms, and it makes the O atoms add to the double bond. So I had a CC double bond. I have an O atom, it's like this. This guy adds, makes this diradical. This does some really strange reaction, and it ends up as, where is it? CH3 plus HCO. And so that's this reaction. I'll explain. The O atom's a triplet. It means the two spins are aligned. So this formed as a triplet. These guys are aligned. But to get here, I think it has to go through a singlet. So there's what's called an internal conversion or intersystem crossing between singlet and triplet. So there's a very strange photophysics going on in this reaction. But anyways, it turns out to be the dominant channel, experimentally verified that this is what you make. And then these guys also can react with the H atom or the OH. In that case, they pulls off an H and makes vinyl radicals, C2H3. And C2H3 reacts very fast with O2 through a bunch of complicated reactions, primarily to make formaldehyde and HCO. This turns out to be the most important reaction for the fuel being finally consumed. So the fuel fell apart mostly to ethylene. And now the question is, what happened to the ethylene? Some of the ethylene reacts directly with O atoms, but most of it reacts with H and OH, which are actually more reactive radicals than O atoms. And they make this final radical, C2H3, and this guy reacts with O2 to make this reaction. This gets down to basically CO, to carbon monoxide. So the ethylene accumulates in your flame, and then when you have enough radicals, enough oxygen, it burns. But because it's accumulated, if you don't have enough oxygen, the C2H3 you formed could actually just recombine and add back to the ethylene and start to polymerize and make stuff that leads to soot. And so, or else you can also, C2H3 can kick out an H and make acetylene, also leading to soot. So this is the crucial species that separates soot from clean burning, is the C2H3 chemistry. Yeah.
So this formaldehyde species, we can find it in all alkene reactions? Or because I read that this formaldehyde is one of the main intermediate species for methane combustion.
Sure. So I'll repeat that. So formaldehyde is a really major intermediate in methane combustion and actually in many other systems too. So you make a lot of formaldehyde. Formaldehyde is very reactive. The CH bonds are pretty weak. And so it's pretty easy to go from formaldehyde to CO. But we make a lot of it. And if you have like an engine, you have cold regions by the walls. And the formaldehyde that's by the walls might survive and be emitted. And that's actually a very bad toxic pollutant. And it's a regulated emission. But most of the time, the formaldehyde in the hot region mostly will all go to CO. And then if you have enough temperature and you have some water vapor around, you'll burn the CO, just like I told before, so the OH will attack the CO and make H plus CO2. But the problem comes up earlier normally at high temperatures, is you've made the ethylene, and you make some acetylene too, and then those guys are accumulating. If the concentration gets too high, they'll actually start to polymerize and make soot. And so the key is you want to get enough oxygen in there to burn it, enough radicals in there to burn all those C2 species and make them instead go to CO and then to CO2 to burn cleanly and not make a lot of soot, because the soot is a really bad pollutant for killing people. It makes the particulates are very bad to breathe. So a key part of the design of combustors and stuff is trying to keep enough oxygen back mixed into the regions where you're pyrolyzing the fuel so you'll burn it before it has time to go into forming soot. The soot can also get burned out. If you make the soot and you have enough oxygen, you can burn it out, but it's much harder to burn soot than it is to burn the molecules. So typically you do better if you can try to just burn it out quickly, not make the soot in the first place. There we go. If enough O2 is present, the C2H3 will burn. Otherwise, it falls apart and makes acetylene, and then the acetylene will typically go on to make soot, and then the soot will tend to kill people. So this is pretty bad. So there's several recent studies that prove this about how bad the soot is. The most dramatic one was there's a river in China where in the old days they had a regulation that the building code north of the river was put furnaces in the houses. South of the river it says it's warm enough they don't need furnaces. So it sets up a very nice epidemiological study of the value of furnaces. So furnaces are great, keep you nice and warm in the winter. You don't get frostbite, you don't get chilblains. The people in south of the river had chilblains. But they also, the furnaces they used were mostly burning like pellets and coal. And so they made a lot of particulates. This was old days. And so the people on the north side of the river have 5 years less life expectancy than people on the south side of the river because they're breathing the particulates all the time. So, and then similarly, they did studies in the United States. This is called the 6 City Study, where it basically showed the same thing, that on the days when the particulate level in the atmosphere was high, the people died. The number of people who died in the morgue was up. The days when it was lower, then it was fine. It was like perfect correlation. So whenever they had a bad event, like the air didn't blow cleanly, there's a lot of particulates, then those days were like the days when everybody died. So it's pretty important to get this right. So this is the very critical branch point for the fuel chemistry. All right. Time is running out. If you have fuel rich and fuel lean, this is a very critical thing. If it's fuel lean, then the carbon will be in form of CO2. If it's fuel rich, you'll typically have CO and hydrogen left. If you have a very fuel rich, if you're only a little bit rich, so the O to C ratio is greater than 1 to 1, then you don't make soot. You could form a little bit, but you basically don't make it. But if the O to C ratio is less than 1 to 1, then what happens is that all the O atoms are sucked up to make CO, and there's still extra carbon left over. And in that case, that extra carbon will tend to make soot, because you don't have enough O2 to burn it out. You can't burn out the vinyl. And you can really see this dramatically when you look at the behavior of a system as you gradually change the air-to-fuel ratio. If you're near stoichiometric, it doesn't really matter. As you get richer and richer, you see some gradual change, and all of a sudden when you get to this 1 to 1 ratio, it's like boom. All of a sudden you start making bushels of soot. You get hardly any energy out of your reaction, because now all you're making is carbon now, not CO2. And so you can really see it. So let's just talk for a few minutes about pollutants. So you can make hydrocarbons. So if you have an engine that doesn't burn all the fuel, you make hydrocarbons. So for example, a typical car engine, a couple % of the fuel is too close to the wall to get burned. And it's cold. And when your piston comes up, it just pushes it up, particularly the stuff in the crevices. So you have a piston that has a little crevice in the gap between the piston and the wall. A little bit of fuel gets down in there. That fuel is too cold, it never burns, it comes out. So if you measure in a city where there's a lot of cars, you can measure all the gasoline components, just the unburned fuel that comes straight through. Some of that stuff gets a little bit oxidized in the exhaust manifold. That's actually make a lot of formaldehyde there. Then you also have evaporation from the fuel. So if you have a fuel tank and has a leak in it or has a hole, the gasoline has a high enough vapor pressure, some of the gasoline will evaporate and come up. So in smoggy cities on summer days, some of the smog is due to that. And that's why we have the gas pumps in the cities in the US have a little vacuum thing that pulls the vapors back in to try to reduce the amount of vapors that are released. Another important pollutant is CO. This is very common in cold start. When you first start your engine up, you tend to make, to get the engine to catch, you intentionally put extra fuel in, but that means you have local regions that have way excess fuel. And the catalyst is not turned on enough when the engine's cold, so it doesn't work very effectively at oxidizing CO. In a modern car, once it's warmed up, the catalyst is hot in the catalytic converter, and that usually oxidizes the CO, so usually not a problem, but just a cold start. But the CO is very toxic, and you always hear about people occasionally getting killed by accident if they are in some region where the combustion is not quite working correctly. NOx makes the brown smog that you see over cities. This is primarily from gasoline vehicles. It leads to all kinds of problems. It makes ground level ozone, which causes respiratory problems and stuff like that. Sulfur, especially sulfur oxides, these are mostly released from coal power plants. In this country, there's emission controls to try to regulate, to reduce this. I think other countries are starting to put them in as well. Probably Europe already has them. Particulates, a lot of these come some from coal and some from diesel. And recently, there's been a lot of regulations to try to reduce this related to, for example, the epidemiology I just told you. And so now modern trucks have particulate traps and other kinds of things to try to reduce the soot formation, or soot release. And then everything makes CO2. All combustion with hydrocarbons makes CO2. Deforestation to make CO2 also. The CO2 is not harmful at all in the near term, but it accumulates in the atmosphere and it causes the greenhouse effect, which changes the climate, which could be pretty harmful. These are maps of the emissions, acid rain. In 2001, most of the rainwater in the eastern US had pH 4.5, which is pretty acidic. pH equals 7 is neutral. The SO2 is also toxic to humans, and the NOx makes smog, so these are all pretty bad pollutants. They're all pretty heavily regulated in the developed countries now. And there's the CO2. So this is the CO2 concentration in the atmosphere versus time, and you can see it's going up pretty fast because we're burning a lot of fossil fuel. This is the anthropogenic emissions over time. You can see it's going up pretty fast because people like to drive, people like to have electricity. This is the historical record of the CO2 level in the atmosphere and the temperature is the blue line. And you can see like a almost perfect correlation between the worldwide temperature and the CO2 concentration in the atmosphere. And then these things are dust in the fossil record. So when the temperature gets high, then a lot of plants die, or because the boundaries where the plants should grow is mismatched, right? And you have like regions become desert, at least temporarily. And then you get a lot of dust. And so you get the spikes of the dust are sort of like just sort of following the peaks in the temperature. So I hope that doesn't happen again. But there seems to be a perfect correlation so far, so this is not very encouraging. And these are just up to 280 ppm, so you can see our concentration now is already, what, 360 something? I think it's higher now, 400 maybe almost.
Professor,
Yeah.
so in the past, what were the causes of those rises of CO2?
I don't know. And I think that there's some theories about it, but I don't know if they really know. In this time period was also the ice ages, so there was a lot of wild stuff going on in the climate. I think in this case, it was better when it was higher because it was a little bit warmer. These were the ice ages when it was low. But I don't know what caused the ice ages to come and go. It's a good question. But the CO2 went up and down with it. All right, so this is, I was just reading the Financial Times last week. And this is a very interesting thing they commented on. They said, basically now there's a consensus that there's sort of a maximum CO2 level that we can put in the atmosphere before we're going to have some wild climate effect. And we're getting kind of close. We're not there yet, but you guys will be alive when we reach this, if we don't change. And so they have a number. Now, the error bar in this number, I don't know. I don't know exactly the number is. But there's some number of capacity that the atmosphere has to hold CO2 before the greenhouse effect is too big. And there's also a number Y, that's how many gigatons of fossil fuel we know where it is underground. It's called proven reserves. And unfortunately, number Y is bigger than number X. So there's two sort of possibilities that might happen. So one is that we burn all the carbon we know where it is, and we exceed the limit and the climate changes. And I would say currently that looks like the most likely thing. But it's also possible that people might realize at some point, this is not a really good idea. And then a lot of those gigatons of fossil fuel that we know where it is under the ground, we decide just to leave there and never dig it out. Now currently, the government regulations all say, in almost every country, that they're going to change their policy and we're not going to wreck the climate. And I think there's a consensus. Most people agree that would be a good idea. But then also, if you look at the stock market prices for fossil fuel companies, every time they find more fossil fuel under the ground, they get more proven reserves, their stock price goes up. And to make the stock price go up, it's not a few people. I mean, a lot of people are buying stock in these companies. Your pension, my pension. Everybody holds stocks in these companies. So people think that the fossil fuel under the ground, knowing where it is worth a lot of money, even though there's too much down there. We can't actually burn it. If we find more, it's even more that we can't burn. So we have this human inconsistency that between what we think we want to do and then the way we act with our money, that doesn't really match up. And something bad's going to happen here. It's either we're going to wreck the climate, or my pension fund's going to lose all its money. So anyway, so I'll just leave that with you. So Financial Times just commented this, and they said, it looks like we're probably going to burn all the fossil fuel and the climate be damned, but it's a risk factor for a fossil fuel company that you might want to think about. Maybe getting more proven reserves is really not worth anything because you're not going to be allowed to burn them anyway. So anyway, that's all I have to say.